Welcome to Spring LIB.
In this exercise, we have a pendulum bob that has a mass m and is initially at the horizontal position, as shown here in blue. It's attached to a pendulum that is at the horizontal, and in that position, theta 0, the initial angle, is equal to 0. Then the bob falls according to gravity, and in the final position, the pendulum bob makes an angle of theta with the horizontal as shown in red. Our goal is to find the tension in the string as a function of the angle theta. Okay? So in order to do that, we're going to need to revisit the concepts of circular motion. Okay? And basically what we need to know is that when a particle is undergoing a circular motion, there are two components to the acceleration. There is a centripetal component, AC, that points towards the center of rotation, and also a tangential component, tangential acceleration AT. The centripetal acceleration is equal to v squared divided by r, and exists even if the speed is constant, and it measures the rate of change in the direction of the velocity. The tangential acceleration, on the other hand, measures the rate of change in the speed, that is the magnitude of the velocity, and is equal to the derivative of v with respect to t. With this information, we can solve the problem. So what I'm going to do is draw the pendulum bob here, and then draw the free body diagram on the bob. So at a certain angle theta, the tension T is pointing in the same direction as the wire, the string, makes an angle theta with a horizontal, and the force, the gravitational force mg, points downwards. Okay, now what I'm going to do is to decompose these forces into a centripetal component and a tangential component. Notice that the force T is already pointing towards the center of rotation, so all we need to do is to decompose the gravitational force. Now notice that this angle here is also theta. So in the centripetal component, which I'm going to call R, we have T minus mg times the sine of theta. And this is equal to m times the centripetal acceleration, which is v squared over r. And then in the tangential component, which I'm going to call theta, we only have the tangential component of the gravitational force, so it's mg times cosine of theta. This is equal to m times the tangential acceleration. Our goal is to find t, this tension here. In order to find t, notice that we need to find the value of the speed v, which is still unknown. In order to find v, I'm going to use the equation for the theta component, where we have that the tangential acceleration, which is equal to dv dt, is equal to mg cosine of theta. I'm going to multiply both sides by v, so we have v dv dt is equal to v g cosine of theta. Now notice that I wrote something wrong here. There shouldn't be this m. It should already have been canceled out. And I'm going to write the velocity v, actually the speed v, differently. I'm going to write it as dx dt, where dx is the arc length element such that dx is equal to r d theta, where the theta is the angle element. So the dt's cancel out, and we have v dv is equal to g cosine of theta dx. Then we have to integrate it. I'm going to integrate it from the initial angle, 0, to the final angle of theta. And in the left-hand side, I'm going to integrate from 0 to v and substitute dx for r d theta. So we have v squared over 2 is equal to g times gr sine of theta. So v is equal to the square root of 2g r sine of theta. Now we can go back to the equation for the r coordinate and substitute it there. So I'm going to isolate t. So I have that t is equal to m times g times sine of theta plus v squared over r. Now remember that v squared is 2 times g sine of theta. So the tension T is 3mg sine of theta. So this is the general tension, which concludes our exercise.